Welcome to a new way of thinking. Let's explore what's possible. It starts with AI teaching machine learning system design, CamelCamelCamel, price tracking system. The problem is to design a price tracking system for online stores, like Amazon. Here are some good questions to ask in the requirement clarification phase. How frequently should the system update prices? Every minute, hourly, daily? Should the system track all products or only user-specified products? What is the expected scale? Number of products, users, and stores? Should we incorporate external factors, seasonality, promotions, competitor pricing? What metrics define model success? MAE, RMSE, alert precision/recall. Let's frame our price tracking system as a machine learning problem. 1. Input. The inputs are the features our model will use to make predictions. For each product, we track historical prices with timestamps, product metadata such as category and seller, store information, and any promotional or seasonal events that may influence prices. These inputs provide the context needed to understand price patterns and trends. 2. Output. The outputs depend on our business goal. We want the model to predict future prices, estimate the probability of a price drop, and potentially recommend alert thresholds to notify users. This allows the system to proactively inform users when the price is expected to reach a favorable level. 3. ML task type. The core ML tasks are time series forecasting for predicting prices and regression to estimate exact price values. Anomaly detection can also be applied to identify unusual spikes or drops, which may correspond to flash sales or errors in the source data. 4. Model choices. Several model types can be considered. LSTM or GRU networks are good at capturing sequential dependencies in time series. Transformer-based models can capture long-range dependencies more effectively. For simpler implementations or ensemble approaches, models like profit or gradient boosting models, XGBoost, LightGBM, may also be effective. Model choice depends on data size, accuracy requirements, and latency constraints. 5. ML objectives and loss function. For regression tasks, the objective is to minimize prediction error using loss functions such as mean squared error, MSE, or mean absolute error, MAE. For price drop alerts, classification metrics like precision, recall, and F1 score are optimized to ensure users receive accurate notifications without too many false alerts. 6. Evaluation metrics. Finally, offline metrics like root, mean squared error, and mean absolute error measure forecasting accuracy, while precision and recall measure alert effectiveness. For business impact, cumulative user savings can also be tracked, linking the machine learning model directly to its real-world value. Let's dive into data engineering and feature engineering for our price tracking system. 1. Data sources. The first step is identifying and collecting relevant data. This includes historical prices from online stores, product metadata such as category, brand, and SKU, information about ongoing promotions or seasonal events, and competitor prices where available. Combining multiple data sources ensures that the model captures the full context that influences price changes. 2. Data collection and cleaning. Data can come from web scraping, APIs, or direct store integrations. Raw data often contains missing entries, duplicates, or outliers. Cleaning involves removing invalid prices, interpolating missing values, and normalizing data formats. Special care is needed to handle dynamic pricing on platforms like Amazon, where prices may fluctuate frequently or change multiple times a day. 3. Time series feature engineering. For predicting future prices, we create features that summarize historical price behavior. Lag features capture past price points at various intervals. Rolling statistics like moving averages, standard deviations, and exponential smoothing help the model detect trends and volatility. Decomposing the time series into trend, seasonality, and residual components can improve forecasting accuracy. 4. Categorical and metadata features. Product-related metadata can be encoded as categorical variables or embeddings. Features like product category, brand, store, and shipping options help the model differentiate between different types of products and stores. Discount indicators and promotional events are especially important for predicting price drops. 5. Derived features and alerts. We generate derived features that directly support alerting. These include price drop percentage relative to historical prices, price volatility metrics, and percentile rankings within historical price ranges. These features allow the model to generate more actionable predictions, such as determining when to notify users about a potential price drop. 6th, data storage and versioning. Finally, storing both raw and processed data is critical. Structured databases or data warehouses are used for storage, while feature stores ensure reproducibility and consistency across experiments. Versioning ensures that the same features used for training are available during inference, preventing inconsistencies and enabling robust retraining pipelines. Let's go through the model architecture for the CamelCamelCamel price prediction system. 1. Input layer. The input layer collects all features engineered in the previous step. This includes historical prices with timestamps, product metadata, category, brand, SKU, store information, ongoing promotions, seasonal events, and derived features such as price volatility, rolling averages, and lag features. This comprehensive input ensures the model has enough context to learn patterns in pricing behavior. 2. Pre-processing and embedding layer. Before feeding the data into the model, we pre-process features. Numerical features are normalized to a consistent scale. Categorical features like product category or store are encoded using one-hot encoding or embeddings, and missing values are imputed. Proper pre-processing ensures the model can learn effectively without being biased by inconsistent data scales or missing entries. 3. Core model. Encoder. The core of the architecture is a time series encoder. LSTMs or GRUs are suitable for capturing sequential dependencies in historical prices, learning both short-term and long-term trends. Transformer-based models can also be used to capture complex temporal patterns and interactions between multiple features, especially for large-scale data across many products. 4th, task-specific layers. On top of the encoder, task-specific layers are added. For regression, these layers predict the next price or a price trajectory. Optionally, a classification or anomaly detection head can predict the probability of a significant price drop, enabling proactive alerts for users. 5th, output layer. The output layer produces actionable predictions. The expected future price, probability of a price drop, and recommended alert thresholds. These outputs can feed directly into user notifications or dashboards. 6. Regularization and optimization. Dropout and early stopping are applied to prevent overfitting, and loss functions such as mean squared error, MSE, mean absolute error, MAE, or Huber loss are optimized during training to improve prediction accuracy. This architecture provides an end-to-end solution for accurate price prediction and intelligent alerting, making the system both predictive and actionable for users. Let's walk through how we evaluate the price prediction model for CamelCamelCamel, both offline and online. 1. Offline evaluation, regression metrics. For predicting future prices, we rely on standard regression metrics. Root mean. Squared error and mean absolute error quantify the average deviation of predicted prices from actual prices. Mean absolute percentage error is also useful to understand relative errors across products with different price ranges. These metrics help gauge how well the model can forecast prices before deployment. 2. Offline evaluation, classification, alert metrics. For price drop alerts, we treat alert prediction as a classification problem. Precision measures the proportion of correctly predicted alerts, out of all predicted alerts, while recall measures the proportion of actual price drops that were correctly predicted. F1 score balances precision and recall, ensuring the model generates accurate and timely notifications without overwhelming users with false alerts. Third, offline evaluation, business-oriented metrics. Beyond traditional ML metrics, we measure business impact. For example, cumulative user savings show how much money users could potentially save by following alerts. Accuracy of discount predictions and alert timing effectiveness ensure that the model provides actionable insights, not just statistically accurate forecasts. 4. Online evaluation, /B testing. Offline metrics are necessary but insufficient for real-world deployment. A/B testing allows us to compare the new model against the existing system using live product data. Metrics such as alert effectiveness, prediction accuracy, and system latency are measured to validate improvements in a production environment. Fifth, online evaluation, user engagement metrics. User engagement metrics indicate real-world impact. Click-through rates for alerts, subscription retention, and conversions to purchases show whether predictions are useful and actionable. High engagement demonstrates that the model improves user experience and trust. 6. Monitoring and continuous evaluation. Even after deployment, model performance can degrade due to changing pricing trends. Continuous monitoring tracks prediction errors, alert effectiveness, and model drift. Retraining triggers can be set to maintain accuracy over time, ensuring sustained system performance. This evaluation framework combines accuracy, usability, and business impact, ensuring the model delivers value to both users and the platform. Let's walk through how the CamelCamelCamel ML model is deployed and served to users in a production environment. 1. Containerization and packaging. Before deployment, the trained model is packaged along with all dependencies using containerization tools such as Docker or MLflow. This ensures the model behaves consistently across development, staging, and production environments. Containerization also allows version control of the model, making it easy to reproduce results or roll back to previous versions if needed. Second, serving infrastructure. The deployed model is exposed via REST or gRPC APIs, acting as a microservice within the larger system. When a user queries a product, the API receives the request, fetches relevant product features, and returns the predicted price or alert recommendation. Microservices allow modular scaling and separation of concerns, ensuring the ML component can operate independently of the web or notification layers. Third, scalability and load balancing. Price tracking systems may experience sudden spikes in queries, especially during sales or promotions. Horizontal scaling allows multiple instances of the model service to run in parallel, while load balancers distribute requests to prevent bottlenecks. Auto-scaling policies dynamically adjust the number of instances based on traffic, maintaining low latency under high load. 4. Caching and latency. Optimization. Caching is used to store frequent predictions, such as popular products, to avoid recomputation. Asynchronous processing pipelines allow predictions to be computed in the background while returning preliminary responses to users quickly. These strategies reduce latency and improve the user experience. 5. Monitoring and logging, continuous monitoring tracks, system health, prediction latency, error rates, and model performance. Drift detection monitors changes in price trends or feature distributions, ensuring timely retraining and avoiding degradation of prediction quality. 6. Continuous deployment and rollback, CI/CD pipelines, automate testing, deployment, and versioning of the model. This ensures safe updates and allows immediate rollback to a previous stable version if any issues arise during deployment. By combining these practices, the system can serve accurate price predictions and alerts efficiently, reliably, and at scale, providing a seamless experience for users while maintaining operational robustness.